it's a great pleasure to have Jerome, who'll be talking to us about spatially modulated phases in AdS CFT.
Well, thanks, David, and it's a great pleasure to be here. And thanks to the organisers, two of which are here, for organising this great workshop and inviting me to be here. I want to talk about some work that I've been mostly pursuing with Aristos Stoinos, postdoc at Imperial. So the general setting of the work is this attempt to deploy the AdS CFT correspondence to study strongly coupled quantum systems that might, or that do appear in a condensed matter context. And one focus has been to consider conformal field theories held at finite temperature and charge density with respect to some conserved currents, and perhaps also inside a magnetic field, and to try and make contact in this context with strongly coupled quantum critical points that appear in condensed matter, for example in high temperature superconductors or heavy fermion systems or optical systems and so on. So how might we want to pursue that particular line of thought? Well, the nice thing about AdS CFT is it says that the phases of these finite temperature systems are given exactly by the AdS black hole solutions that have the appropriate asymptotic behavior. The appropriate asymptotic behavior corresponding to putting it at finite charge density and a magnetic field, or with respect to some deformation of some other relevant operators that might appear in the field theory. So this very difficult quantum problem has been turned into a classical problem of constructing these black hole solutions. So once you've constructed them, and it's important to construct all of them, not just the first one that you can, you should calculate the free energies, compare all the free energies of the black holes with the same asymptotic data, and then from that determine which one has the smallest free energy, and then you determine the phase diagram. So that's the general program, and as I said, this point about all AdS black holes is a key point. So it still is a difficult question, but it's a much more simple question than the original quantum question. So the kinds of questions that we're interested in is what type of phases are possible, and in particular, the way this game is going is to try and recreate phases that you do see in real condensed matter systems. What type of zero temperature ground states are possible? So you construct the black holes and then all the way down to zero temperature, and then look at the long distance behavior of these gravitational solutions, and then deduce something about the far infrared behavior of the zero temperature ground states. And in particular, at zero temperature in the far infrared, one can find new emergent conformal symmetry. One can find not just conformal symmetry, but other scaling symmetries like Lifshitz, Schrödinger, and in fact the list is open. We don't know what the full set of scaling solutions are in the far infrared. So one question is, what are these ground states, these possible ground states in a holographic context? And one way of finding them is to find the black holes and then run them down to zero temperature. There's other ways you might approach that problem too. So one wants to pursue this, and then once we have, the real power of AdS CFT is that linear response theory allows you to work out various transport quantities like conductivities very easily by just solving linearized equations in those backgrounds. I think it's particularly interesting to construct top-down solutions, which are solutions of d equals 10 or d equals 11 supergravity. You might also consider a brane probe approach, but I'm particularly interested in the d equals 10 or 11 supergravity solutions. So how would you find those solutions? Well, there's a whole bag of tricks to find solutions of d equals 10 or d equals 11 supergravity, which goes back for obviously many, many years. But one technique which has had some significant development over this period, motivated by trying to find some of these solutions, is that of consistent Kaluza-Klein truncations. So a consistent Kaluza-Klein truncation is when you reduce on some internal space to a theory such that the modes you keep don't source any of the modes you throw away. So the theories of the lower dimensional supergravity solution give you exact solutions of the higher dimensional one. And for example, and I won't give a full list of the developments here, but for example, on Sasaki-Einstein 7 spaces from 11 dimensions to 4, and Sasaki-Einstein 5-dimensional spaces from type 2b to d equals 5, there's been these significant progress in constructing extensions of obvious supergravity theories which have been very useful for constructing the solutions, some of which I'll describe later. So in this top-down approach, I think it's definitely, this program of AdS-CFT has certainly led to new insights into d equals 10 and d equals 11 supergravity. There's a new class of black holes which have been constructed and discovered precisely by trying to put into d equals 10 or d equals 11 supergravity condensed matter ideas. So I think that there's no doubt that AdS-CFT is certainly is enriching the kind of landscape of string M theory. Whether or not it actually is useful for condensed matter, I mean, we'll have to see. I think the jury is out on that question. Okay, so what I want to do is briefly just give a bit of a survey of some of the phases that people have looked at, and then the second part of the talk will eventually be focusing on one particular model where I'll map out some of the details a little bit more. So let me just briefly review how you might look for superconducting phases in AdS-CFT. If you want to construct black holes asymptotically to AdS that correspond to a superconducting phase. So we consider a conformal field theory in 3 or 4 space-time dimensions, for example, and we wanted to have a holographic AdS4, AdS5 dual. And we also want the conformal field theory to have a global U1 symmetry. So global U1 symmetry by the dictionary is dual to a gauge field in the bulk. And the key point is to have superconductivity, or more precisely superfluidity, because we have a global U1 symmetry in the CFT, is that we want some object, some order parameter, to spontaneously break this global symmetry. We want an order parameter or a charged field in the bulk that will spontaneously break the global U1 symmetry. And there's 2 types of superconductors or superfluids that people have looked at. The first one was so-called S-wave superconductors, and there the order parameter has 0 angular momentum. So 0 angular momentum as an order parameter, so that corresponds to a scalar field in the bulk. So you can try and construct asymptotically AdS black holes that carry electric charge and also have this charged scalar hair. And the nature of this charged scalar hair gives rise to the spontaneous breaking of the global U1 symmetry. And this was pursued by these people, and well, one paper was with Julian Sonner, who's somewhere in the audience, and myself and Toby Wiseman, who put this in a top-down context. How about P-wave? Well, P-wave is also seen in real systems, for example, helium-3, heavier fermions, strontium ruthenate, and other systems. And there, in these P-waves, the order parameter has angular momentum 1. So how do we model that in the context of AdS-CFT? Well, there's been 2 approaches to this. One is you start off with some SU2 gauge fields in 4 or 5 dimensions. So these are SU2 gauge fields in the bulk. And you take a U1 in that SU2, and you take the background system to be charged with respect to that U1. And then the 2 W bosons, the other 2 generators, are the charge fields which correspond to the L equals 1 order parameter, which you would like them to get active. So you'd like black holes carrying this W boson hair. And Steve Gubser constructed these guys. The issue of spontaneous is actually incredibly important, and for people who aren't familiar with that, I'll precisely spell out what makes it spontaneous rather than explicit breaking. But another example of P-wave superconductors is in 5 dimensions, you can use a charged self-dual 2 form, and that was pursued by this collaboration down here. And it's actually this last one, these charged self-dual 2 forms and P-wave superconductors, which are, in the example I spell out later, I'll be focusing on. So all of those examples are in the context of looking at conformal field theories at finite chemical potential with respect to the global U1 symmetry. Or equivalently, the black holes in the bulk are carrying electric charge. But it's not, holographic superconductivity is not restricted to that context. You can also switch on magnetic fields. So in fact, have purely magnetically charged black holes that spontaneously want to form charged hair, either scalar hair or charged vector hair. And in some examples that were worked out by these people, one can see, map that out explicitly. And interestingly, both occur for n equals 4 supersymmetric Yang-Mills theory. So supersymmetric Yang-Mills theory, n equals 4 Yang-Mills theory is not, it probably has very little to do with any condensed matter systems. However, it's a great paradigm example to look at in almost any setting. And I think there's much more to be done actually on this line of trying to work out what the phase diagram is of n equals 4. That would be one concrete problem, which would be nice to nail down. Yes?
Are there any P-wave superfluids? No?
Yes, that was what I put up on the previous slide. Helium-3 from
Those are
superfluids. Helium-3 is, yeah.
Uh-huh. There is a P-wave, there is another.
Yes, yeah. Good. So yes, so holographic superconductivity driven by magnetic fields, which are slightly counterintuitive, one can have, and is actually very, very natural in the context of AdS CFT. Okay, so that's a quick review of the superconducting story that people have looked at. Let's move into this spatially modulated phase, which might be less familiar to people. So, in fact, it's actually very common in condensed matter to have systems that spontaneously break translation invariance, and that's what spatially modulated phases mean. For example, charge density waves, there's just a spatial modulation of the charge density. Spin density waves is a similar spatial modulation of the spin density. And the important thing about the spatially modulated phase is the order parameter is now no longer associated with zero momentum, but non-zero momentum. And if you think for a moment, obviously, if we're saying in a context of strongly correlated electrons, we have a lattice, so there we have explicitly broken translation invariance. That's not what's of interest here. What's of interest is that in the low energy, long wavelength degrees of freedom, you get some emergent translation invariant degrees of freedom, which then spontaneously break. So in particular, the spatial modulation, the wave number associated with spatial modulation is not determined by the symmetry of the underlying lattice in the so-called incommensurate spatial modulated system. So that's the kind of the context we're thinking about. With
even so, Jerome, you wouldn't normally think of waves as electromagnetism, Maxwell's equations. You don't say they break translation invariance because there are wave solutions.
No, this is the vacuum. This is the ground state.
So a wave is the ground state.
Yes. So there's no time dependence here. It's just, I mean, think of the spins just literally in the ground state. Exactly, like ferromagnetism or antiferromagnetism, but you can have something more complicated. Yes, yeah, in fact, the language is slightly confusing. There are density waves which do describe low energy oscillations of other ground states, and that's not what we're talking about. So yes, yeah.
Calling it incommensurate if just the periodicity of the spin density wave is not that of the...
Exactly.
But it doesn't matter if it's much larger or much smaller, that doesn't matter. If it's just slightly off, the physics will be the same really?
I think it's, I mean, the way I describe it is just some emergent scale that appears. And actually,
so
I don't know if...
think it should be much larger than...
Yeah, I think typically it will be larger, exactly. But there is also commensurate spatially modulation as well, which it actually is fixed by those lattice wave numbers.
These would be theories without Lorentz invariance.
Yes, exactly.
Because I guess in Lorentz invariant theory it's possible.
No, so we're spontaneously breaking translation invariance in particular. Yeah.
How do you know it's impossible in Lorentz invariance?
I think there's a theorem that you can't break Poincare symmetries, spontaneously in a Lorentz invariant field theory. So I think Coleman, there's a theorem of Coleman's and
Actually, I wasn't agreeing with that. So yeah, sorry, I wasn't aware of this
Exactly the
theorem.
Heronian limit, where the speed of light goes to zero.
Can't you just do something stupid like have quadratic derivative terms with a negative sign plus quartic ones with a positive sign? That must surely do it.
quadratic term, just a scalar field theory with a negative mass square.
Minus d phi squared plus d phi to the 4.
I guess you probably want unitarity or something with a lower bound on the energy of the vacuum. Probably some assumptions like that, but I thought under fairly general assumptions like that, there's a theorem that in any Lorentz invariant field theory you can't break Poincare symmetry spontaneous.
Thanks. In any case, the examples we'll be looking at, it's at finite chemical potential, so we'll explicitly break that part. Okay, so what else? Well, this modulation doesn't have, I mean, the obvious thing to think about is to have some stripes, but you can have other modulation where you have checkerboards or hexagonal structures. And in these chiromatic liquid crystals, and also this manganese monosilicide helimagnet, you can have a helical structure. So this underlying structure takes a helical form. And in fact, it's this helical structure, for reasons you'll see later, which is the one in the example that I'll discuss in detail, that we'll see. And finally, I just mentioned that QCD, going back to work of Rubikov, it's been suggested that that also is in a chiral wave state at high baryonic density. That seems to be still somewhat of an open issue. Okay, so that's a quick review of spatial modulation in condensed matter, and just briefly in QCD. So it is widely seen. It's also possible to have superconducting spatial modulation. And this goes back to a very old work by Full, Ferrell, Larkin, Ochinnikov in the 60s. And an FFLO phase, well, what they were thinking about was just a variation of BCS, so it's all weakly coupled. And you want to construct a situation when the Fermi momentum for the spin-up particles is slightly different from the spin-down particles. And a simple way of doing that is to switch on a magnetic field. So you just separate out the two Fermi momentum, and then hopefully the pairing is strong enough to produce an order parameter with non-zero momentum, and then you want that to condense, and then you get these FFLO phases. But because typically magnetic fields suppress superconductivity, this is a very delicate thing in practice. And it seems to me the status is almost 40 years later, that this heavy fermion system, the cerium compound, is perhaps the best. It seems very controversial. There's many papers which they say they've seen an FFLO phase, and then no one else refers to those papers. And if you look at Wikipedia, this is the one that seems to be the least controversial. In any case, I think but there's no doubt that, I mean, this mechanism is the FFLO mechanism is so simple that it's widely, I mean, it's not controversial that they should exist. It's just delicate to prove that you're actually really seeing it. Okay, so with all that little background, can we study them using holography? And actually, you might think it's very complicated, but some aspects of it are very simple. And there's actually been now quite a bit of work done on this by Aristos and I and my student Cristiano Pantaladou. But it started off with actually a couple of papers by Tomokos and Jeff Harvey, and another one by Nakamura, Oguri, and Park. So taking d equals 3 or d equals 4 conformal field theories at finite chemical potential with respect to a U1, then there are spatially modulated phases. And a little bit like the superconductors, I might just get this pointer. A little bit like the superconductors, you can also, if you switch on a magnetic field, that's enough also to drive a spatially modulated phase. And by looking at various cases, we've now found examples that have charge density waves, examples that are spatially modulated and also are superconducting or superfluid, and specifically ones with a p-wave helical order. And there's variations of all these things in different contexts of d equals 10 and d equals 11 supergravity. So there's quite a bit of work that's been done here, and I don't have time to review that, but I did want to advertise that there's quite a lot known, and then I'm going to choose one example to pursue a bit further. So the main conclusion is spatially modulated phases are not exotic, and they might actually be the typical ground states of holographic matter at finite charge density. All of the work I just mentioned, it all shows the existence of these new phases by doing a linearized perturbation about a known phase. And you find that at some critical temperature, that phase becomes unstable, and a new branch of black holes must exist. So that's just using a linearized analysis. And for quite a while, I thought that to go beyond this, you would have to solve PDEs. So after all, these black holes, they depend on the holographic radial direction. But now if we're going to give a modulation in one of the other spatial directions, naively it looks like everything's going to depend on the radial direction. Well, not naively, it will depend on the radial direction and this extra other direction. So now it depends on two coordinates, and if it's two coordinates, that sounds like you need to solve PDEs. So as a general statement, that's true, and I think where this program has got to, or is going, is that there's an enormous class of black holes in holography that can be accessed by solving PDEs. So that's obviously technically daunting, but I think it's interesting that that landscape's been opened up. So that's interesting, but there's something nice you can do. And it's very, very simple, but it took us a year and a half to realize. And if you know what Bianchi 7.0 is, then that might already be ringing some bells. So for the rest of the talk, I want to describe actually construct some fully back-reactive black hole solutions. So constructing solutions that do actually depend on a radius and also an extra direction. And the examples will be these helical p-wave superconductors. And as I just said, it'll rest on the fact that they have something called Bianchi 7.0 symmetry, which I'll remind you of or tell you about if you've never come across that. And what's nice about the particular examples, we get lucky in the sense that we can construct the finite temperature solutions. We continue the solutions down to 0 temperature, and the 0 temperature limit is completely regular. And in the far infrared of these 0 temperature solutions, they approach some scaling solution. And the scaling solution is of a type that was, it's similar. It's similar to a type that was found by Iyazuku and collaborators. Okay, so from now on, I'm just going to focus on one model. So is there any more questions on the general story? Okay, so this is the model. So we're in 5 dimensions, 5 bulk space-time dimensions. My theory is just Einstein-Hilbert, a cosmological constant, which I've taken to be 12, a kinetic term for a gauge field, and this is the only unusual piece. There's a charged 2-form, C. H is its 3-form field strength. So F is dA, and H is dC plus IE AOHC. So C is a charged 2-form. Carries charge E, and this M parameter here turns out to be the mass of the oscillations, excitations of the C field, of the 2-form. So the class of models I'm considering is here, so it's specified by two free parameters, M and E. And the equation of motion for the 2-form is this self-duality equation, which is possible in odd dimensions. So star H is Im times C. So star H is a 2-form. That makes sense. So we can certainly solve this equation by setting C equals A equals 0, and then we just basically get this part of the theory. So AdS5 with A equals C equals 0 is a solution. So that AdS5 solution is meant to be dual to a 4-dimensional conformal field theory. And if you look at oscillations around that 4-dimensional conformal field theory, around the AdS5 vacua, A is corresponds to a global U1 symmetry of the CFT, and in particular A is dual to the conserved current. How about the 2-form? Well, the 2-form oscillations, as I said, they have a mass m about the AdS5 vacuum, and if you just go through the dictionary, this means that they're dual to an operator with dimension 2 plus m. And it's being a 2-form, it corresponds to a self-dual tensor operator. Now, that stage of...
How did that M come about, the dimension formula?
This one?
Yeah, it's a bit unusual.
It's just the standard. It's just the standard dictionary of reading it. I mean, the mass of for a scalar field, for example, the mass well, as you know, is naturally associated with the dimension of the operator.
Oh, I see. So that M is just usual mass parameter.
It's just really usual mass parameter.
Okay, sorry. Okay.
Yeah. Okay, and certainly some people in the audience, this part of Lagrangian is completely familiar, but maybe not to everyone. But so let me just say that these naturally arise in string theory compactifications. So for example, if you compactify an 5-sphere from type 2b down to 5 dimensions, you get precisely that model with E equals 1 on root 3 and M equals 1. In fact, for the most interesting part of what I'll be talking about, these values aren't relevant. However, closely related models can be obtained, for example, by reducing D equals 11 on 6-dimensional manifolds down to 5 dimensions. So these couplings are naturally associated with 5-dimensional gauge supergravities, and they're either exactly embeddable into string theory or very closely related to that. But I won't be emphasizing the top down any more than that. Okay, so let's now consider this CFT, this 4-dimensional CFT at finite chemical potential. At high temperatures, it's described by this AdS5 AdS Rice-Nordstrom black brane solution. So we have the time coordinate, the radial coordinate, and the spatial sections of the black hole are flat. And this function g, which appears here and here, is just a function of the radial coordinate r. And the gauge field is given by this just standard electric form, and the 2 form is 0. And the function g, here it is, it's r squared, and the r plus appears and mu appears. So asymptotically, it goes like r squared, so that's the AdS5 boundary, and when r is r plus, where you see the gauge potential vanishes, that's the black hole horizon. So this is a black hole which describes the CFT, and if you work out the Hawking temperature is just given by this expression involving r plus and mu. So it describes the CFT at this temperature and finite chemical potential. More precisely, it's the high temperature phase. If there's other black holes, you have to compare them and see which one has the smallest free energy. But at high temperatures, almost certainly this is, it's not a theorem, but almost certainly this is the only one. And clearly we see that the phase is spatially homogeneous and isotropic with a full Euclidean symmetry. What else about this solution? Well, as it's well known, if you go to 0 temperature, this black brane solution approaches AdS2 cross R2 at the horizon. So in particular, the conformal field theory has a non-zero entropy density at t equals 0, basically just the size of this R2 factor. So non-zero entropy at 0 temperature is, in a usual thermodynamic context, is considered to be unphysical. In the context of AdS-CMT, it's also been argued that maybe it's a profound feature of the whole program, and interesting fermion spectral functions are associated with AdS2 cross R2. I won't be discussing that any further, but it's very often the case that this AdS2 cross R2 solution, or this region, is not physical because there's other black holes which appear and have less free energy. And in fact, for this model, that's exactly the case. So the signal that this AdS2 cross R2 is irrelevant and the AdS Rice-Nordstrom is no longer relevant at low temperatures is the AdS Rice-Nordstrom black brane becomes unstable at some critical temperature. And the quickest way to find that this is happening is to go down to the AdS2 solution at 0 temperature, look for linearized perturbations, and see if there's any modes that violate the BF bound. So if they violate the BF bound in the AdS2 region, as you heat it up, they will lead to some instabilities at finite temperature, all the way up to some critical temperature where you'll get a 0 mode. So that's just a quick pass to see that the AdS Rice-Nordstrom is unstable. To actually see at which critical temperature the AdS Rice-Nordstrom becomes unstable, you have to do linearized perturbations around the AdS Rice-Nordstrom black brane itself. So that's what one does. This is the first pass, and then you work harder to do this. And this program is the program I was referring to when I said that people have shown that many of these spatially modulated black holes exist, is by pursuing that little program. And the final step would be construct back reactor black branes. I didn't put on that slide. So let's look at this for the model that we have. So let's consider the AdS2 cross R2 limit of the Rice-Nordstrom black brane solution. And after some playing around, one can consider this perturbation of the 2 form, which looks a little bit complicated. We have C1 times dt plus C2 dr. This cos kx1 dx2, sin kx1 dx3. There's another function C3 of r dx1 wedge, this 1 form here. And the point, or one of the points, is the equations of motion for the 2 form, the linearized equation of motion, imply that C1 and C2 are fixed by C3. It's just this first order nature of the equation of motion for the 2 form. So really, the degree of freedom to focus on in this 2 form is this piece here. And then it starts to look, okay, it's not completely obvious that you should be taking these factors, but it looks like just some wave in the kx1 direction. And as k varies, you will just get a tower of different modes. So, that's the answer. That's for C, and C3 satisfies a second order ODE around the AdS2 cross R2 solution. And then you just work out what its mass is, and it turns out to be this formula. So you get the usual m squared, it was a mass m2 form in the AdS5 language. There's a k squared, just the usual k squared contribution to the mass. There's a minus e squared, charge gives a negative contribution to the mass. That's usually what drives superconductivity. And the self-duality equation gives this feature. This is a key point, a term that's linear in k, and it involves e and m in that ratio. So in particular, the smallest mass, the smallest AdS2 mass is at non-zero k. And that's the key point. So at k minimum, that's when this AdS mass is smallest. And if you substitute that back in, you find that if the charge is big enough, then the BF bound is violated. So if we're in this regime, then the AdS2 region is no longer stable, which implies that the AdS black brane must be unstable at some finite temperature. And we expect this characteristic modulation to be to appear. So now let's do the same calculation in the AdS Rice-Nordstrom black brane, and you'll notice very little change between those two slides. So we go back to the AdS Rice-Nordstrom black brane solution. We take exactly the same linearized perturbations. So C1 and C2, C3 are functions of R. Once again, C1 and C2 are fixed by C3, and C3 satisfies the second order ODE. And now I'm going to restrict, just for ease of presentation, that the mass is 1. Okay? So we're now in the AdS Rice-Nordstrom black brane setting, so I need to give boundary conditions for this field C3 out at the AdS5 boundary. And it turns out that C3 is a constant. Oh, sorry, I did it back to the front. Sorry. This is the boundary condition for C3 at the black hole horizon. It's a constant plus a piece that it vanishes. It's just analytic at the black hole horizon. Out at infinity, the expansion for m is 1 is C3 goes like a piece like proportional to R, and then a piece like proportional to 1 on R, and so on. And these two coefficients, these two constants, correspond physically to a deformation of the conformal field theory by the operator dual to the 2 form. And CV corresponds to the operator acquiring an expectation value. So if CD was non-zero, it means you've taken your CFT and you've explicitly broken both the U1 symmetry and also the translation symmetry by switching on the appropriate operator. So I'm going to demand that's 0, so I don't want any explicit breaking. And then I want to demand that CV, well, I want to inquire whether I can have a situation where CV is non-zero. So this is what spontaneous breaking of both the translation symmetry and superconducting symmetry is, the U1 global symmetry in this context.
Jerome, what property is modulated here?
So we see that we're going to break the translation invariance in the x1 direction.
The x1 direction.
So this is invariant in the translations in x2
Is
and
this
x3.
the only criteria that goes into this ansatz, or are there some other assumptions made to parameterize delta C in this fashion?
No, so I think, this would be the general kinds of oscillations of C3 just in the bulk. You could just expand in some sort of roughly plane waves. This is obviously picking out the x1 direction, you could pick out the x2 direction, and so on. So there's some basic mode analysis, and I'm just focusing on one mode and wanting that to become active. So it's actually a good point that you could have many. In a linearized analysis, you find one mode that's unstable, but if you find later another one, at a linearized level, you can superpose them. So a question becomes, if you just construct from the first one some black holes, you should really, once you've done that, go back and see what happens if you added a second one. And that's this issue about stripes versus checkerboards. You have some modulation in one direction, you could have modulation in another direction. Maybe the real thing is a checkerboard and not just stripes. So that's a harder question.
Is there some polarization choice?
Yes, there is a polarization choice as well. And I'll explain that in a second.
Can I think of this as related to Gregory-LeFlamme stability? If there was a brain wrapped on the thing that you're doing the reduction, and then we know as we shrink, you can get this sort of goes into like drips.
Yeah, I don't. There's some similarities, but there's some differences. So one of the differences is that there's no that instability then becomes time dependent. There's a non-uniform branch of string solutions that Toby Wiseman found, but they have higher free energy than the original guy. If it had been the case they had lower free energy and existed for lower temperatures, then you would have gone down to a critical temperature, gone onto this non-uniform branch. In that particular context, that's not what happens, and it becomes time dependent all the way down to this bubbling and whatever.
That wasn't in AdS though.
No, that was, but sorry, that's somehow, that's in a black hole language,
Yeah.
that's somewhat equivalent. So there's some similarities, but some differences.
I mean, there's a critical dimension above which then this picture changes. And
That's true, isn't it? 11 or something, or 13.
13 and a half.
That's it. Yeah, thanks. Yeah, so at this stage, I've just picked out some mode, and I want to see if I can set CD equals 0, and have these boundary conditions at the black hole horizon and at R is infinity, and see if I can solve the equations of motion, linearize the equations of motion, and I can. So this plot, well, I've plotted. Remember, m is 1 just for definiteness, and I've plotted various values of e. So what have I plotted? This is the temperature. This is the temperature of the rise to Nordstrom black brane solution, and this is k, the wave number. So k, the wave number, is the one that's appearing here and here. So the statement is that when k is about 1.6, as I'm cooling down the AdS rise to Nordstrom black brane solution, exactly at that critical temperature, a mode with k equals 1.6 becomes unstable, or is actually a 0 mode. And below that temperature, that mode is tachyonic. Over here, if I lower the temperature down a little lower, then more values of k become tachyonic. And this diagram looks a little bit exotic. It's actually the standard thing, except the standard thing would be that the origin would be sitting here. So for any kind of phase transition that people have looked at in holography, you always get this diagram with a dependence on mode number. It just happens to be centered around k equals 0. So if you think about it, the mode that people look at, say, an S-wave superconductor becomes tachyonic at a certain temperature. If you add a little k dependence to it, the mass is going to be increased, so the critical temperature is going to go down a little bit lower. So this in itself is nothing strange. It just hasn't, I suppose people didn't appreciate it before. The strange thing is that it's shifted away from k equals 0. That's all the novel thing. Is that clear? That's kind of one of the key points. Okay, so I said that in C, this answers, I think, Dan's question, that everything really depended on C3. C1 and C2 actually would fix by C3. So this is really the degree of freedom to focus on. So C3 had this form. And if we now think of x1, x2 directions just plotted out in the plane, and then I'll do a Hodge duality. So x1, x2 points in the x3 direction, and x1, x3 points in the minus x2 direction. You see that when x1 is 0, so sitting back here, this points purely in the minus x2 direction. And then as I go along the x1 direction, this sines and cos just trace out this helical structure. So that's why, that's the pictorial reason why we've got a helical structure here. And it's called a px wave structure in the literature. And for people who know, there is something called px plus ipy, and you can ask me about that afterwards. So these particular perturbations do correspond to helical p-wave order, or black holes with p-wave order, and that are also superconducting. Why superconducting? Because C was also charged. Okay, so that's the linearized analysis. How do we go beyond this and actually construct back-reacted black hole solutions? And as I said at the beginning, one would have thought, well, the black hole is going to depend on a radius and this x1 direction. That sounds like PDEs. And it's not PDEs for a very simple reason. We're going to use the Bianchi 7-0 Lie algebra instead of the Euclidean algebra. And this has 3 generators, Bianchi 7. It's translations in the 2 and 3 direction. And in the 1 direction, it's a translation supplemented with a rotation. So that's 3 Killing vectors, and they satisfy this Lie algebra. And being so we have this 3-dimensional Lie algebra, and it's taking this Lie algebra, we want to construct an ansatz using the dual left invariant 1 forms. And if you just play around a little bit, you can convince yourself that these 3 1 forms are left invariant by the action of this Lie algebra. And what you see is exactly the kind of object that we saw in inside this linearized perturbation. So the key idea is then to use these 1 forms to construct an ansatz, and since there's 3 of them, it's homogeneous, then we can, the whole ansatz will just depend on several functions just depending on the radius. So here it is, in fact, the ansatz. So for the metric, well, it's minus g, and I'll put in a function here, another function of r here, f dt squared, g to minus 1 dr squared. And now I'm using these Bianchi 7 invariant 1 forms instead of the Euclidean invariant 1 forms. So omega 1 squared, omega 2 squared, and omega 3 squared. Alpha is another function of r, and h is a function of r. And just, I've written what omega 1, 2, and 3 are here again. This is just the x1 squared, and these coses and sines appearing in omega 2 and 3 appear here. So you'll notice that if alpha was 0, then omega 2 squared plus omega 3 squared, put that together, you just get the x2 squared plus the x3 squared. So if alpha is 0 at the AdS5 boundary, then this will just naturally look like the AdS5 boundary. The usual one.
Could you have different modulations for omega 2 and omega 3? I mean, or was that regularity or what? What sets those exponentials?
Yeah, this was a minimum ansatz which was consistent. So yeah, you could add more things in and inquire about what happens, and it's a good question.
If it's homogeneous, how have you broken translation rates?
Well, Euclidean symmetry has been broken down to Bianchi 7. That's the simple point. Why we don't have to go to PDEs, which is it took us 18 months to realize.
I mean, it's homogeneous but non-isotropic.
Yeah.
Yeah, well, that sounds more like breaking rotation invariance of translation.
Well, you preserve those 3 Killing vectors, 2 translations, and a translation supplemented with a rotation.
And the point is you can get anywhere else, right?
Yeah.
So in that sense,
It's homogeneous.
so I would say you haven't broken translation invariance, I would say. Because you can get anywhere else. Every place is the same.
Depends on what you mean by translation.
No, but by homogeneous, it's every place is the same, right?
Yes,
So
but not by translations. Translations with a rotation.
see, we're into semantics now. I
And
should let you carry
location.
on.
Okay, and this ansatz for the 2 form is just written in terms of now left invariant 1 forms, is exactly what we had before. And A, it turns out to be sufficient just to be allowed to be purely electric, and A is just a function of R. So the point is that using these left invariant 1 forms on Bianchi 7, 0, there's an ansatz which depends on G, F, H, alpha, C, I, and A, which are just functions of R. So if you substitute these into the equations of motion, we just get ordinary differential equations, which is not so bad. So what do we do? Well, we have to impose boundary conditions at AdS5 and also the black hole. So at AdS5 boundary, this is the expansion that we impose. So let's have a look at this. So C3, C1 and C2 are again determined by C3, and actually the other functions. C3 has this CV times 1r to the m behavior. And this, again, is this demanding this means that we're spontaneously breaking the global symmetry and the Euclidean symmetry. So, and CV then corresponds to the expectation value of an order parameter at wave number k acquiring an expectation value. So that's what this is. How about in the gauge field? So we have the gauge field is AdT. This is the chemical potential, and Q is the charge density. So Q here corresponds to the charge density of the CFT. So this is an expectation value of the current in the state at finite temperature and chemical potential.
I have one more question also. So you can only ever break at the same time superconductor. I mean the U1 and the translation.
Yes.
You can't break them independently.
So in this model, yes, in this model.
Which is a bit different from this FFLO.
Yes.
I mean, where you really could do the things independently.
Exactly. It would be nice to have a version with just a scalar field, yeah.
And we have two-parameter model, right? M and E.
Yes.
E doesn't figure out here somehow.
Yeah, so it appeared, and then I've kind of suppressed it. Remember, at this AdS2 mass analysis, that's sort of the very first starting point, E had to be bigger than square of m was square root of 2 before you'd even see instabilities. And the critical temperature at which the instability set in depended on E, and it's sort of sitting there in the background. So it's still there.
It seems somehow curious that they both have to be broken at the same time. I mean, couldn't you have had some Bianchi type symmetry that is triggered by only a neutral type order parameter?
I think Bianchi is the only one that includes
In a sense,
Euclidean.
it sounds like it's not the minimal thing that you could have gotten. It's got some extra feature. Is that you want breaking?
Yeah, it's a good question, but I don't know how to do it. Let's have a look at these other functions. So G, H, F, and alpha. Not the details aren't too important, but they all appeared in the metric. And their fall off is, well, we want it to be AdS5 in the UV, so that's what these R squared and R terms are. Alpha goes to 0 as R goes to infinity. But there's these parameters C alpha, CH, M, and CH appearing there. So I've identified what CV, Q, and mu are, but these other parameters, what do they correspond to? Well, if we work out the stress tensor, the holographic stress tensor, we find of the four-dimensional conformal field theory takes this form. So M and CH appearing in the energy density, M and 8CH appearing in the pressure in the x1 direction, M and now a spatial modulation gives the pressure in the 2 and the 3 directions, and there's also this shear in the 2, 3 directions given by C alpha, which is appearing here. So all of those parameters have a natural physical interpretation, and they're naturally associated with the fact that we have this helical motion. You expect these pressures in the 2, 3 direction to change as you go along the x1 and x2 and x3, along the x1 direction. Well, you can quickly check that this is traceless as you expect for a conformal field theory. And, well, these calculations are actually quite a bit of work, but I'm not going to tell you any of the details. But the free energy, after you do all the counter terms, is just proportional to minus m. So if we can find, so we want to demand this, we have this asymptotic behavior at infinity, we demand it's regular at the black hole horizon, you've got to go and solve ODEs numerically, and Aristos is a master at this. And this is the final picture of the black hole solutions that were constructed. So in fact I've chosen M is 2 and E is 2 just for definiteness. So this is one particular model, and we calculate the black holes. So what have I got here? I've got wave number k along this axis, I've got the free energy along this axis, and the temperature along that axis. So if we just push this into the plane for a second, let me just flash this up again. Remember, this was the temperature versus k, and let's just fix attention on one curve. That was the critical temperature in which the AdS rise to Nordstrom became unstable. That curve is this curve here. So that's the curve in which these new black holes come into existence, which is what the linearized analysis said. So for each k, what we do is we construct the black hole solutions all the way down to 0 temperature. And then the vertical axis, the new feature here, well, the fact that we've filled in the curve by the existence of black holes, is the free energy. And what we find is the black hole that minimizes the free energy goes on this slight relaxed walk in the K space. So the wave number of the pitch of the helical order slightly, or the wave number K, slightly decreases as you go down to zero temperature. And actually that's one of the things in AdS, well, in condensed matter. In these helical orders, they do measure this pitch and how this pitch changes with temperature. And they do one thing they do is complicated Monte Carlo simulations to try and calculate and determine that, the way in which that changes. But here, we're actually getting this exactly, albeit by a numerical, solving ODEs numerically. So this red line in this two-parameter family of black hole solutions represents the thermodynamically preferred configuration of this system, at least in the context of the problem we're looking at. There could be additional black holes which we don't know about. So that's the main result. And if you go down all the way to zero temperature, you get down to a smooth solution, which is a domain wall. It's AdS5 in the UV, and in the IR, it's a smooth scaling solution, which I'll put up on the next slide or two. And that blue line is a construction of those domain walls directly, and their free energy. And then we're seeing that the black holes that we're constructing exactly do map onto those domain walls.
How does this wave vector compare to the linearized analysis that you did and the minimum?
Yeah. So this curve, remember, that was the linearized analysis.
It was, I see. So it's not quite at the minimum. Is that?
So that was the critical temperature in which the spatial modulation first appears, and the wave number just sort of moves off slightly down to about, I don't know, a little bit down there. Okay, so I think I'm saying similar things here. So here's the diagram. The red line is the minimum free energy black holes of the system. Clearly it's a second order phase transition, well clearly at least as far as this picture goes. And on these two plots, for that red line branch of solutions, I plotted CV, which is corresponds to the expectation value of the order parameter of the two form, and K is the wave number versus temperature. So this plot is the usual one that you come down to some critical temperature, the expectation value switches on, and then goes down to some finite value, and the dot corresponds to the domain wall. And K just starts at, well, times 10 at 5.5, and then sails down to 3.0 monotonically. There's an interesting technical point which, if anyone's noticed, is that I'll just mention it just in case, because something we don't understand. CH appears here in this expansion of H, and it appears in various components of the stress tensor. It's a fact that on the red line, on this two-parameter family of black hole solution, CH is non-zero, but on the red line itself, CH is zero. Just a bit of an aside. Okay, let me then just say something about the t equals 0 solutions. So as I said, at t equals 0, the black holes become smooth domain walls, interpolating between AdS5 and a new scaling solution, which I've written up here. So this solution here is an exact solution of the equations of motion. So what I've got r to the 2z times dt squared, dr squared on r squared, a constant times w1 squared, omega 1 squared, which is the x1 squared. And then we have r squared, and these were these other Bianchi 7 left invariant 1 forms. The 2 form is basically as it was. C3, C1, and C2 are just constants now. And one of the functions, this r to the z appears here again, and a is a constant times r to the z dt. So all the objects appearing in here, z, h naught, alpha naught, etc., are all constants. And z, for example, is 1.99. And this solution, which people are familiar with, looks a little bit like the Lifshitz solutions that Katru and collaborators constructed. But it's a little bit different too. It's a little bit different because we have this Bianchi 7 structure in the metric. But the main point to emphasize is that it's invariant under this scaling symmetry. So we scale t with the lambda to the z. This is the dynamical exponent z. x2 and x3 with the lambda to the power 1. And x1 doesn't scale at all. And if we scale r in this way, you can just quickly check that that whole solution is invariant. So the picture is you cool down, you put the CFT at finite temperature, finite chemical potential, you cool it down to a critical temperature, you go onto this superconducting, spatially modulated helical phase at 0 temperature. A very long distance description is described by this emergent scaling symmetry. So it's a very nice story for this model. Okay, so just to wrap up, so these are the first back-reactive black hole solutions that are spatially modulated. And this was possible because we could exploit this Bianchi 7 symmetry in constructing the ansatz. Well, I think I said the rest there. One thing that would be nice to do is to look at linear response in this background. And chiral pneumatics, which have these helical order, have these interesting optical properties. So if you shine polarized light onto chiral pneumatics, sorry, you shine light, they reflect one polarization back, for example. So beetles, these iridescent beetles, that's also associated with chiral pneumatic phases of liquid crystals. So that'll be fun to pursue, I think. What about other examples? I mean, this is just one, and just briefly I'll mention a couple of other ones. Well, let me just quickly pass over this, but there is this thing called P plus IP order, and it's quite closely associated with this P wave order, and we would like to see which one is actually thermodynamically preferred. So we're looking at this at the moment. A simpler model, which is actually the one that Aguri and collaborators first looked at, was Einstein-Maxwell-Chern-Simons theory. So there's no two form. We're in 5 dimensions, and the Chern-Simons drives the spatial modulation. And one can do quite a similar analysis. A difference from what I've described is that the t equals 0 limit of the black hole solutions is a bit unclear. So that's an interesting open issue we're looking at. There's another example which has a nice top-down embedding, which is SU2 cross U1. But more generally, well, perhaps more interestingly, there's an example in 4 dimensions, and it has an axion and gauge fields, which is driving the spatial modulation. And it's an interesting one because it leads to stripe phases and charge density waves. But this example, unlike the ones I just mentioned, will involve solving PDEs. So this trick of Bianchi 7 is quite special. So yeah, but just going in that same direction, the main message I think to convey is that I think there is a rich landscape of spatially modulated phases in the context of AdS CMT, and if you put the system at finite chemical potential magnetic field, some of them we can explore in detail by using this Bianchi 7 trick. Some others will require solving PDEs, but I would hope, in fact, particularly the people who spend a decade trying to solve Gregory Laflamme got interested in these, because I think it's a more interesting question than that. Okay, thanks.
Questions?
Jerome, at the beginning of your talk, you said that the jury was out with regard to how applicable are these results in condensed matter physics. Can you elaborate slightly on this? I mean, if you were to compare these results with real systems, how far does that go?
Well, yeah. I mean, the first part of the question, I suppose, is there are condensed matter physicists working using holographic techniques. And there was, in fact, I don't know if you were here, but there was a workshop here a couple of weeks ago, and there was some leading figures in the field actively working on this. There's interesting connections. Probably one of the things that people have been very interested in is fermion spectral functions in the context of holography. And there is controlled examples of reproducing some spectral functions which, from a condensed matter side, had just been postulated phenomenologically by Varma and Littlewood. So that caused some interest and excitement. But if we take this model as a template, it's some large n limit. Well, I didn't quite emphasize the top down, but say if we're in the context of n equals 4, or sorry, not n equals 4, but we're in this context of some top-down that we have some control over. We're in some large n limit of some gauge theory, and condensed matter has emergent SU2, SU3 gauge fields that they look at. That n goes to infinity, all this adjoint matter. It's quite different. So I don't know. There's a few other people in the audience who might have a different opinion, but I think it's the only tool we have to study these strongly correlated systems in some sort of controlled form. So maybe there will be some general messages, but whether we'll actually be able to nail a model on the head and say, here's a high temperature superconductor, and here is the holographic example that describes it, that might be too far.
Can I have a follow-up question? After
Why not? Go on, Evan.
if you don't mind. Here you have the charge, U1 charge, true form.
Yes.
Which comes from type 2b on S5.
Yes.
Are there also models where we have non-abelian charged forms, like two forms, say? And if there are some like that today, come from string theory, and what applications can you envisage for such objects, if they're there?
Let's see. So I suppose in 7-dimensional gauge supergravity,
You expect them there?
there are 3 forms which are charged. There are 5-dimensional representation of SO5.
Let's stick to 5 dimensions. Are you aware of charged two forms in 5D?
I can see you and Paul will be the people that probably ask.
What's the answer? I'm lost.
If you don't know, no one else does.
No, I know the answer.
You know the answer to
No,
the
no,
question.
no, not top to down. No, I don't. That's the question. No,
It's,
top down, I don't know. I have no idea.
I see.
I can construct them from first principles, but not top down.
I see.
But suppose you are given such a model.
Could you do something similar?
This is what you're doing. What could they lead to? Can you make a guess?
Well, I suppose you'd have some the extra gauge symmetry would be some global symmetry in the field theory, and you would perhaps switch on some chemical potential for those global symmetry currents.
But there are no candidate condensed matter systems?
Yeah, I think.
On abelian
Yes.
global symmetry?
I think not.
It's always U1 somehow.
U1 is meant to be electromagnetism.
Of course.
Of course, it's global in the context of AdS CFT, but then a story is, well, if you weakly gauge it, it's very similar to actually much of the phenomenology of superconductivity. So I'm not sure. I mean, one thing is, it's just that holography naturally gives us an enormous spectrum of models to look at and analyze. And it might be, I mean, you can be, the most optimistic thing is perhaps something brand new is what's going to actually inspire the condensed matter theorists. So maybe they'll start looking for things with larger flavor symmetries and be able to construct them using optical lattices or something. Julie?
So do you have thoughts about making statements which kind of instabilities are actually the ones which thermodynamically are relevant?
You
I
mean
mean, in the
preferred?
sense that, I mean, even in cases where we have a specific dual theory, for example, you could ask, I mean, it could be a question independent of this. What mechanism dominates? I mean, will it actually at finite chemical potential have a modulated ground state, or will it have a ground state that breaks some of the symmetries,
Yeah.
or a combination thereof?
Yeah, that's a very good question. So, for one example, as you know, AdS 4 cross S7, when there's more freedom and there's more channels for different types of instabilities, we had a crack at trying to address that. But you find lots of multiple branchings, you find lots of different second-order transitions, you find first-order transitions, and there didn't seem to be any guiding principle.
It's also not really a question that you can answer by looking at the linear instability somehow.
I mean, you might be in a
They're all
context...
there, so they're all options. It's like
Yeah.
it's the menu, but you need to choose one.
The linearized instability should give you the first phase transition. And then you might...
Then all bets are off somehow.
Well, you might be able to, yeah, I agree. At the moment, with what we understand, but you might hope there's some context where the one that's highest does sail down to 0 temperature. But there's examples where that's not the case. So it's a problem. I mean,
I wonder if there's maybe a different approach, some mechanism that one might envisage, which tells you actually the answer, rather than having to follow all these. But I suppose that's what condensed matter physicists have been trying for a long time, and
yeah.
haven't really done.
One from Kim Young.
So you had E and M coming from n equal 4 theory. Is it unstable or not?
So actually, for n equals 4, this one is not, it's stable. So it has to be, it's some other top-down ones where it becomes unstable.
Right.
And this, I didn't catch this twist tensor quickly enough. So when your CH was 0 for the
Yeah.
M of the energies, what did it? Oh, I see. So it renders
It's the pressure and the energy density.
pressure.
Yeah.
One has no understanding for.
Yeah, I mean, we're obviously in this diagram, we're minimizing in this two-dimensional moduli space of black hole solutions the free energy against K. And just formally, you can sort of see that this happens. But so it's there's no doubt it's true. But it'd be nice to have some other understanding, because it could have been a priori. It could just be some small number. It could be any number. So I think there must be something going on there.
Yeah, you just answered in response to Kim Young's question. You said there's a top-down model coming from M theory on some 16.
Yeah.
Which does.
Yes. Yeah.
Do we know the dual field theory?
So those models, if you take 5 branes and you wrap on a 2 surface, it's a bit like these Goethe and Mendelssohn theories. You wrap on a 2 surface, that gives you down to a 5-dimensional theory. And in the cases where they're conformal, then there's a 6-dimensional internal space.
Let's thank the speaker again. Thanks.